Now we're going to talk about general relations that are valid in equilibrium. And here I have a small box that's a reminder. We have two important results. The derivative of natural logarithm of number of accessible states with respect to energy is beta, and with respect to an external parameter x is minus beta x bar, where capital X bar is the mean value of the change or shift in energy levels with changes in the external parameter x. So let's say that we have this most general situation. We have a system A that has energy E, and we have system A prime which has energy E prime, and the system A plus A prime, A star, is isolated, so there is no thermal interaction with the rest of the universe. The total energy, therefore, E plus E prime, which is the total energy E star, this is a constant, and the total number of accessible states, omega star, will be a function of the energy that system A has and a number of external parameters, x1, x2, let's say all the way up to xn. These are my external parameters. And in this system I have a thermally conducting piston which is free to move, that is connecting system A to A prime, and this basically implies that in this interaction I have both heat exchange and work present. And at equilibrium we're going to have the mean energy of system A to be its most probable energy, E tilde, and the mean value of the external parameters x alpha will be equal to their most probable values, such that we're going to have a sharp maximum in the number of accessible states for the star system with these values of energy and external parameter values. So there is a sharp maximum in the number of accessible states at these values. And let's talk about the equilibrium conditions in more detail. So basically I would like to find out the criteria for equilibrium. So let's say that here from the most general situation where I had n external parameters, now I'm saying A and A prime are characterized by a single external parameter V, which is the volume. That is volume V. And for this external parameter, the restrictions on the system is that the total energy E star is a constant and the total volume V star is a constant. So the isolated system A star also has a constant volume. The number of accessible states to system A will be called omega, and it's a function of its energy and volume. So I call omega as a function of E and V the number of states that are accessible to system A, and this will be in the energy interval E to E plus delta E. So I have a sufficiently small delta E that the number of accessible states is not changing significantly, and volume values in the interval V to V plus delta V. So a small change in this volume by an amount delta V does not affect the number of accessible states, to a good approximation. So corresponding number of accessible states for the prime system will be omega prime, which is a function of E prime and V prime. And because E prime is E star minus E and V prime is V star minus V, I can write it also this way. So this is the corresponding number of accessible states to system A prime. And the total number of accessible states, omega star, for the star system will be the number of accessible states to system A multiplied by the number of accessible states to system A prime. So these are happening at the same time, so the joint probability of having this situation is basically corresponding to the total number of accessible states, which is the product of the accessible states to system A and A prime. So if you look at the natural logarithm of the total number of accessible states, you get natural logarithm of omega plus natural logarithm of omega prime. Since entropy is k ln omega, so if I multiply this with k, the Boltzmann constant, I will find that the total entropy S star is S plus S prime, entropy of system A and entropy of system A prime. And we know that due to the second law of thermodynamics, in equilibrium we must have the maximum possible entropy for the total system. The most probable situation corresponds to the energy and volume values where the total number of accessible states omega star and therefore the entropy S star is a maximum. This is second law of thermodynamics. We need to maximize the total number of configurations that gives us this situation. So that is basically the equilibrium situation. So if you look at this equation and take its differential form, you will find that d ln omega star must be equal to d ln omega plus d ln omega prime, and for the total number of accessible states to be maximum, we need to have this to be 0. This is basically maximizing omega star. So the change in ln omega is due to change in energy and change in volume. So it is del ln omega del E at constant volume dE plus del ln omega del V at constant energy dV, because omega is a function of two variables, energy and volume. So Looking back at our results, del ln omega del E is beta, del ln omega del X is minus beta X bar. So I can substitute these results for d ln omega. So let me remind you that del ln omega del V, which is, so for X is equal to V, is going to be you can also write this as del ln omega del E del V, and this is going to be equal to beta times what is del E del V. So this is, if this is for a if you consider the first law of thermodynamics, which says dE is equal to d bar Q plus d bar W, if you take the derivative of energy with respect to volume, this is basically del E del V is going to give us beta time, so it's going to give us d bar V W dV, and this is the work done on the system. So remember, so d bar W is minus p bar dV. So if you take the derivative, you get minus p bar. So this del ln omega del V is actually equal to minus beta times x bar. So it is minus beta times x bar, and this is equal to beta times d bar omega dV. So we find that this is going to be equal to minus beta x bar will be equal to minus beta p bar. So x bar is going to be equal to p bar according to this expression. But for del E del V, I'm considering the work done. So this is for work done by the system, so that therefore I need to introduce a minus sign here. So this is going to be plus, so x bar will be minus p bar. So this is the mean conjugate force, mean force that is conjugate to volume, and this is the force applied by the gas, applied on the gas, so therefore it is minus p bar. So this is on the gas, or on the collection of particles in this system A. Actually, this is something we talked about before. So we gave this as an example. If you remember, x bar is the mean generalized force on the system conjugate to external parameter V, and d bar W is minus p bar dV. It is also equal to x bar dx. So that is the because x bar dx is dE, so we find that x bar is minus p bar. That is the force mean generalized force conjugate to volume acting on the system. So indeed we find that x bar is equal to minus p bar, and We can substitute this result into this equation here. So let's see what happens. For d ln omega, I have del ln omega del E, which is beta, multiplied by dE. So I have beta dE. And then the second term, I have del ln omega del V, which is minus beta x bar, which is plus beta p bar multiplied by dx, so it is dv. So this is what we find. And similarly for ln omega prime, we will have the same result, beta prime dE prime plus beta prime p bar prime and dv prime. So d ln omega prime, you can write this as beta prime. D for E prime, I can write E star minus E, and for this P prime stays the same, and for the volume I can write V star minus V. So d ln omega prime will be equal to minus beta prime dE, because E star is a constant, and it will be equal to minus beta prime P prime r dV, because V star is a constant. So if you add d ln omega and d ln omega prime, you find that this is going to be equal to beta minus beta prime dE and plus beta times p minus p prime dV. And this must be equal to 0 at equilibrium, and that has to be for any dE and dV values. So this is basically extremum point in the number of accessible states omega star. So that comes from maximizing omega star. And that implies we have two conclusions. Beta must be equal to beta prime and P must be equal to P prime, or we can write the absolute temperatures of the two systems must be the same. So the fact that we need to have the same average pressure exerted on the gas, P and P prime should be the same, and the same absolute temperatures on both sides. This is automatic consequence of maximizing S star. So this conclusion is basically very important. So it tells us the condition for equilibrium is to have the same absolute temperature and the same mean pressure on both sides of the boundary between the two systems at equilibrium. So let me summarize what we said. So we had a system A and system A prime. A has energy E, volume V. A prime has energy E prime, volume V prime. Total system is isolated and has fixed boundaries. So fixed boundaries, and therefore the total volume is a constant and the total energy is a constant. And I call the total number of accessible states omega star. Omega star is a function of energy of system A and also a function of the external parameters x1 to xn in general. And if I have a thermally conducting piston which is free to move, I have both Q and W present in this interaction. So heat exchange and work are both possible. And equilibrium condition will be corresponding to the mean energy of system A to be the most probable value and all the external parameter values should have a mean value, which is the most probable value. And this will correspond to the total number of accessible states, omega star, having a sharp maximum. And I called omega the number of states accessible to system A in the energy interval E to E plus delta E and volume interval V to V plus delta V, and omega prime is the corresponding number of accessible states to A prime. The total number of accessible states is the total possible number of configurations where I can have combinations of configurations in system A and A prime, and this is the product of the two. And therefore the total entropy S star is the entropy of system A plus entropy of system A prime. An equilibrium condition is the most probable situation where I have energy and volume values that will give me a maximum in the entropy or the total number of accessible states due to the second law of thermodynamics. And in order to have a maximum in the total number of accessible states, the derivative of the total number of accessible states giving me the differential d ln omega star at this values of E and V should be equal to 0. So this is at E is equal to E tilde, V is equal to V tilde. We must have d ln omega star to be 0. So because the number of accessible states is a function of energy and volume, d ln omega is del ln omega del E at constant volume dE plus del ln omega del V at constant energy dV. So del ln omega del V is del ln omega del X is minus beta X bar. So del ln omega del E, which is the beta times X bar, minus X bar, so minus beta X bar. So this basically gives me the generalized force conjugate to volume X bar to be a minus P bar. This is the pressure not applied by the gas but applied on the gas. So X bar is the force acting on the system so that its energy levels are shifting. So this is basically minus the pressure applied by the gas. So it's minus P bar. And if I write d ln omega substituting these results, beta is del ln omega del E, so it is substituted here as beta multiplied by dE, and then I have del ln omega del V is beta times P bar, and then I have dV. And similarly I have for d ln omega prime beta prime dE prime plus beta prime P bar prime dV prime, and using V prime is V star minus V and E prime is E star minus E, I can write d ln omega prime as minus beta prime dE and minus beta prime P bar prime dV, and the total must be 0. Automatically gives me they must have the same beta value or same absolute temperature, and they must have the same pressure, mean pressure P and P prime. So that is going to be the equilibrium condition.